Hello everyone, this is Rui PCB, your trusted PCB partner. Today our topic is the impact of vias on four-layer boards, via optimization strategies and structures. Welcome back to the department focused on via impacts in four-layer boards. In the previous video, we analyzed how vias through parasitic inductance and parasitic capacitance become a bottleneck for high-speed signals. Today, we'll discuss more practical content, how to tame these parasitic effects by optimizing design, especially via structures, to ensure our high-speed lines work smoothly. First, let's review how parasitic inductance and parasitic capacitance are formed. In vias, parasitic inductance is generated on the copper plating of the inner wall, while parasitic capacitance is formed between the via and the surrounding ground or power plane. So, what are some of the important general design principles that we can follow in order to successfully reduce the unwanted parasitic effects of vias? In high-speed PCB design, we try to follow the following principles to optimize vias. First, minimize the number of vias. This is the most effective strategy. Try to reduce the number of times high-speed signal traces switch layers, if possible. Lay out the entire high-speed bus or sensitive signal lines on the same layer, or only use a small number of vias for necessary transitions. For example, in this circuit, these differential pairs are generally high speed, and you can see that only this differential pair uses two vias because there was really no way to route around it. Most of the others do not use vias and are directly connected as much as possible. So this is what we mean by minimizing vias. Second, choose the appropriate via size. The hole diameter and pad size are not necessarily better the bigger they are. If the hole diameter is too large, it may increase the body resistance, and if the pad is too large, it may cause discontinuity in the return path. Usually, for high-speed signals, smaller hole diameters and smaller pad diameters are chosen to reduce body parasitics. Of course, you also need to consider manufacturing costs. PCB manufacturers have limitations on via sizes, and they may start charging extra below a certain size, with the cost increasing as the size gets smaller. So bigger is not always better, but neither is smaller always better. You need to consider all factors together. Additionally, regarding return vias, for high-speed signals, a return ground via must be placed close to the signal via. This ground via can provide the signal with the shortest and most direct return path, greatly reducing the current loop area and the parasitic inductance of the layers. The return via should be placed as close as possible to the signal via. For example, in our case, this can be considered a type of return via. Of course, it is also designed for differential pairs, with vias placed around the signal via to form a surrounding structure. Third, remove unnecessary pads. For high-speed signals, if a via passes through layers that do not need to be connected, these unconnected pads and via barrels form stubs, which introduce additional system discontinuities. Especially long stubs can cause severe reflection. Back drilling technology can remove unnecessary stubs in vias, thereby significantly improving signal integrity. This is a better method. This advanced but more expensive manufacturing process is mainly used in extremely high-speed scenarios. For example, it is only used for frequencies above 17 GHz because the cost is too high. Fourth, avoid drilling holes around vias. Drilling holes in the reference plane around vias is done to prevent short circuits, but if the area of the drilled hole becomes too large, it will damage the reference plane around the via and increase the impact of low-level currents on return signals. According to the minimum requirements of the PCB manufacturer, this so-called clearance is set as a keep-out area around the via, and there will be through holes. Therefore, the value should not be as large as possible, but rather as small as possible. However, its limit is also determined by the manufacturing capabilities of the PCB factory. When do we need to use optimized wave control timing, such as in the process of ground shielding? For the most sensitive and highest speed signals, we may need more advanced wave control optimization technology. What does the ground shielding process mean? A circle of tightly arranged ground vias is made around the high-frequency signal via to form a shield. Its function is that these ground vias can provide better electromagnetic isolation for the signal, further reduce and radiate EMI, and reduce crosstalk with other signals. At the same time, it also provides an additional return path for the signal via. The application scenario is mainly used to set signal breakthroughs for highly digital signals, or as breakthroughs on the dividing line when dividing the ground plane in areas that require strict isolation. I have not set up signals on this board, so there is no such breakthrough. It is also similar to the differential breakthrough. Then there is the use of the differential pair breakthrough. For the differential pair, the two signal breakthroughs are required to be symmetrical and the number is equal. Contract vias should also be placed next to them. So that's it. Check the branch line. One line cannot be punched and the other line is not punched. If you need to punch, both lines use vias and punch ground vias around the two vias. Today we took an in-depth look at the impact of vias on high-speed signals and learned how to mitigate these issues by minimizing the number of vias, optimizing their size, improving return paths, and using ground shielding strategies. Mastering via optimization techniques is a key step to successfully designing high-performance multi-layer boards. I hope this content helps you enhance your professional level in PCB design. If you enjoyed this video, please subscribe to my channel for more videos. Thank you, everyone.